Yeah, today we are very happy to have Teng Fei from Rutgers, New York, giving a talk on degeneration of Calabi-Yau threefolds and three forms. Yeah, thank you.
Right. Thank you, Simon, for the introduction and the invitation. It's a great pleasure to speak at CMSA, and unfortunately, I wasn't able to speak in person due to like the flight delay. So I'm just going to talk on Zoom. So here's my plan. So this is based on, actually, I should update this. This is based on a few papers on archive and some ongoing projects. So I'll start with the motivation and which is the SYZ conjecture. And then I'll mention how my setup is different from the usual setup or for the SYZ. And I'll talk about degeneration three forms. This is purely from a linear algebra point of view. And after putting some natural integrability conditions, we are going to see that the almost all kinds of geometric consequences in the SYZ conjecture can actually be derived canonically from certain degeneration of three forms. And finally, we're going to introduce this the more general setup, which I call Nilpotent-Jordan Calabi-Yau geometry. And I'll also mention some examples as well. Okay, so let me know if there's anything you want me to clarify. So the main motivation for this work is the famous SYZ or Strominger-Yau-Zaslow conjecture. And this conjecture has many versions, I believe. And so I'll be kind of vague at places. So roughly speaking, the SYZ conjecture says that near large complex structure limits, so these are the places where the complex structure degenerate most. Calabi-Yau manifolds admit special Lagrangian torus vibrations with singularities. And moreover, the vibration is semi-flat, and the base of this vibration admits an affine structure with singularities. Together with a Hessian metric solving the real Monge-Ampere equation. So here being semi-flat means because these fibers are torus, it just says the induced metric on the fibers on this torus are all flat. And third, the mirror manifold can be constructed by taking the dual torus vibration of this Lagrangian torus vibration with quantum corrections. So this is like the geometric, I guess, principle to construct the mirror Calabi-Yau as predicted in mirror symmetry. So there are actually lots of aspects of these SYZ conjecture. For example, from a more algebraic geometric point of view, there's this Gross-Sieber program. And there are also lots of work from a more analytic point of view, like Gross-Wilson, the work of Gross-Wilson, Joyce, Collins, Jacob Ling, Liao Li Ling, Yang Li, Halpern, Johnson, Mason, McLeary, and Baldilla, Pelka, etc. So there are lots of work on this SYZ conjecture. It's still not fully solved, but there are many recent progress. But what I would like to address today is to answer some, I would say, some naive questions. So these all comes from degeneration of Calabi-Yau structures, like large complex structure limit. So a basic question is why Lagrangian fibrations or even weaker foliations, they arise from such degeneration. And also, usually when we are talking about these degeneration of Calabi-Yau manifolds or just complex manifolds, it's like we have the generic fibers are smooth, but the complex structure, they may degenerate. So the central fiber is usually a singular variety. But in the SYZ conjecture, all the predictions are not about the central fiber, not about the singular object. They are actually predictions about smooth objects that's very close to the central fiber. And why is that? And also, there's some other ingredients in this SYZ picture, like the semi-flatness of the fiber metric, and also the real Monge-Ampere equation satisfied by these Hessian metric on the base, and so on. So my goal today is to present a direct explanation to some of these ingredients involved. And for simplicity, we work with complex dimension 3, though many, and this is the dimension I guess the physicist cares most, but many results actually generalize to higher dimension. Okay, so that's the motivation. And then I'm going to introduce my setup to study the SYZ conjecture, which is very different from the usual setup. So the usual setup for studying, I guess, SYZ conjecture or in general degeneration of varieties is we consider a polarized degeneration of Calabi-Yau threefolds, for example. That is to say, we have a family of Calabi-Yaus mapped to let's say open unit disk in C, and we're filling this the central fiber, which could be singular. But our setup is actually much more naive. It's more in the flavor of a differential geometry. Is that because when we're talking about the Calabi-Yaus, if you from the more algebraic geometric point of view, we usually ignore the Kähler structure or the symplectic form. Instead of we may just replace that by a polarization, which is just like we work with this certain say cohomology class or like ample line bundle instead of a fixed a given representative. Here what we do is we fix a symplectic manifold. So that's the underlying manifold of these Calabi-Yaus. These Calabi-Yaus, they are all diffeomorphic to each other, and but the complex structure there, the Calabi-Yau structure there, are different from place to place. But what we do is we fix this underlying smooth manifold M, and also we fix the symplectic form. And we want to consider a family of Calabi-Yau structures on this fixed symplectic manifold. So a basic thing is that we can easily pass from the usual setup to our setup because all the smooth fibers are diffeomorphic to each other. Therefore, by a ad hoc choice of gauge, we can all identify them with the same manifold M. And because this polarized family is that so you're choosing a relative, for example, relative ample line bundle over this family. So the first Chern class gives you the Kähler form. but this first Chern class is discrete, so actually all these symplectic forms or the Kähler forms, they have the same de Rham cohomology class. Therefore, they all can be pulled back to the same symplectic form by applying Moser's trick. So this is like the standard technique in symplectic geometry. Therefore, this is again by choosing by another choice of gauge. So that is to say, for some complicated or totally unknown choice of gauge, we can just assume all the fibers of this polarized family of Calabi-Yaus with the polarization to be the same symplectic manifold. Okay, so that's how we pass from the usual setup to our setup. But there's some disadvantage. For example, by just choosing this, we are losing track of monodromy. So there's also some advantage, that is now we have something more structure fixed. We have the symplectic form fixed. It's easier to take certain limits, and that is the thing I'm going to explain in detail.
Teng Fei, just to be sure, you fixed the symplectic structure, but you changed the metric and you changed the complex structure so that they still satisfy the same Kähler relation with respect to the fixed symplectic structure. That is correct.
That's right. That's right. We allow the complex structure to change, and the complex structure and the symplectic together, they determine the Kähler, the metric, the Riemannian metric. Okay. So here's the full statement of our setup. It's like we fix this symplectic manifold, and we consider a family of Calabi-Yau structures. So what do I mean by this Calabi-Yau structures? They're actually just the holomorphic volume forms. These are sections of canonical bundles, which are nowhere vanishing. These forms, they are differential forms, complex valued. So they have real parts and imaginary parts. So I'll just call the real part phi and the imaginary part phi hat. And T just denotes this family. It could be a real family, or T could be a real parameter or a complex parameter. And actually, this encodes all the information you have, because the complex structure J is actually determined by this holomorphic volume form, capital omega. Of course, if you know the complex structure, you can form the canonical bundle. So, and this holomorphic volume form would just be a section of the canonical bundle. But on the other hand, if you just know this holomorphic volume form as a complex valued 3 form, it actually determines the complex structure, because you can ask, okay, what are these anti-holomorphic vector fields? Those are the vector fields. If you take the interior product with capital omega, you get 0. So the holomorphic volume form determines all these anti-holomorphic vector fields, or anti-holomorphic tangent bundle, and its complex conjugate will give you the holomorphic tangent bundle directions. And the splitting of the full complexified tangent bundle into the holomorphic and anti-holomorphic bundles is the information you need to cook up this complex structure. So basically, J is just the operator which acts as I on holomorphic tangent directions, and minus I on the anti-holomorphic tangent directions. So J, the complex structure, is determined fully by the complex value 3 form. And this works for any dimension. But there's something special for complex 3 dimensions. So for Calabi-Yau threefolds, actually, the full complex volume form is determined by its real part. And I will refer this as the Hitchin's construction, though it was probably not first discovered by Hitchin. But this was, I guess, the most accessible explanation of this is in Hitchin's paper on 3 forms in 6 dimension. So that is to say, if we are in the real dimension 6 or complex dimension 3, actually we can canonically construct the imaginary part from the real part. Hence, we can get the full complex volume form. And I will explain that in detail in my next few slides. So just trust me at this moment. All we need is the real part. And this real part is not something random. It's a primitive 3 form, meaning that the wedge of phi with the symplectic form omega, little omega, is 0. Because if we have a Kähler metric, this omega would be a 1,1 form, and this phi would be a 3,0 plus 0,3 form. So the wedge is obviously 0. But it's not a random positive. It's not a random primitive 3 form. It has to be positive. The positive is in the sense that we can actually this phi is actually the real part of a complex volume form, and from that you can form this J, and this complex structure together with a symplectic form together, they yield a positive definite metric. And there's a very precise state meaning of being positive. You can write down, but I think it's not that important. The important thing here is that this being positive is an open condition. It's like if you have something positive, then all the nearby ones are also positive. And another fact is that actually we can assume a little bit more. Is that we can also assume that this complex volume form or its real part is Ricci flat, meaning that the corresponding Kähler metric is Ricci flat. And the reason we can assume that is that we can run, if this is not Ricci flat, we can run what's called the type 2A flow. And this is a geometric flow introduced by myself and Feng and Sebastian Picard and Xiangwen Zhang. It's like we can apply these geometric flow with the initial data we have, and at the end we'll get something Ricci flat. And so it's basically like we can optimize this holomorphic volume form or the complex structures such that it stay being compatible with the symplectic form, but the metric is going to be Ricci flat after the optimization. And the new complex structure is actually diffeomorphic equivalent to the old complex structure limit, to the old complex structure you have, but not symplectic morphically equivalent. And this Ricci flat condition can be fully interpreted as some differential equation satisfied by phi and the phi hat. It's just both of them are closed, and that the norm of this 3 form is a constant. and that's just like saying the induced metric on the canonical bundle is flat. And
Sorry.
the
So your definition of Calabi-Yau structure is like not necessarily integrable Calabi-Yau structure, right? That's why you don't
uh,
get Ricci flat for free.
so if you don't put integral conditions, it's just a SU3 structure. It's like the first few dots. But once you impose this Ricci flat condition, it's automatically integrable. So this two conditions
Yeah.
guarantee that the complex structure is integrable.
And then the flow you are saying, is it like a Laplacian flow?
Um, well,
Like a D star flow?
I think I would say it's more complicated than the Laplacian flow. It's like this is a flow of three form with a fixed symplectic form, and the but the leading so this is a weakly parabolic in the sense that it's actually more degenerate than the usual Ricci flow case. So it's like besides this symmetry coming from the diffeomorphism, there's some extra degenerate directions um, that's where make the short time existence very difficult. So I say it behaves. Its induced flow uh, on the Riemannian metric or the curvature is like a scaled version of a Ricci flow, but the flow with itself on the three form level is more complicated than the usual Laplacian flow.
Okay, thank you.
Mhm.
Also, quick question: the T you said can either be real or imaginary. Is there any imaginary complex, real or complex? Is there any difference between these two cases, given that you said that you're giving up monodromy, basically?
Uh,
Or,
so in the future, I'm going to work with the T as a real parameter, and um, uh, I guess that's the reason we lose track of a monodromy if you will only work with real parameter.
yeah,
Uh,
yeah.
um,
Okay. Does the type 2A flow of anything type
this
2A string theory?
yes, it's motivated by this complexification of type 2A superstrings with flux. So the equation there is, so the stationary point of this flow are basically the solutions to the type 2A equations in this with non-trivial flux.
Sorry, have you said how do I think of the flux in this
Uh,
setup?
so
What?
in that case, it's like this in the type 2A equations with flux, this complex structure may not be integrable. You may have something and then there are singularities like the branes coming from special Lagrangians. So it's still the symplectic form is still integrable, so omega is closed. But the complex structure is not necessarily integrable, and this non-integrability is accounted for the presence of certain special Lagrangians calibrated by
Yeah.
the real three form. So in that case, the real three form, the phi is closed, but its imaginary part may not be closed, and yeah, maybe that's all I can say.
It's good. Thanks.
Um,
Already helps.
yeah, sorry. Okay, so the question I want to say, so is there a limit of this family of Calabi-Yau structures? Here I'm saying the Calabi-Yau structure is fully encoded in its real part, and this is important because there are many examples where we can actually take a limit of the real part, but the imaginary parts may blow up. So this limit here allows us to consider things we don't see if we take the limit of the for example the complex volume. Okay, and so our setup is like we assume that we have such a limit, and this convergence is smooth away from some singular locus. And if that is the case, then this limit, which we call phi 0, should be a degenerate primitive 3-form satisfying strong integrability conditions. Because all these phi t's, they can be because they come from Ricci flat Kähler matrix, they themselves satisfy strong integrability conditions. Their limit also does so. But of course, there's when we are talking about the holomorphic volume form instead of complex structures, we have some extra freedom. That is, we can rescale this holomorphic volume for by some constants. And by doing that, we can help this real part to converge. But of course, we don't want this to converge in very stupid way that everything is going to 0. If that's the case, we cannot. But if you just let the scaling become smaller and smaller in the fast enough rate, you can always make this limit to be 0. But that's something we want to avoid. So what we want is we want this phi t to converge in a specific way with rich geometric information we can extract from the limit. So the limits cannot be too bad, cannot be too trivial. And in order to achieve this, we have to understand what are the possible degeneration of primitive 3-forms. And we want our setup to be some specific kind of degeneration of 3-forms. And that's a purely linear algebra problem. And this is very classical math. So we begin with a 6-dimensional real vector space. Let's call it capital V. And we take a 3-form on this vector space. That's phi. And there's a natural general linear group action on the space of 3-forms. And all the orbits of this action are classified. And this has been known for a long time. It was first due to Rachel in 1907, but that's the case where over complex numbers. And later, Gurevich classified all the real orbits. And this has been rediscovered for many times by many authors. And this is an incomplete list. And I learned most of this from Robert Bryant's paper, which is, I think, the most, I think this is the easiest one to read. So the Rachel's paper, I think it's in German, and Gurevich is in Russian. And so I cannot read those. And anyway, so here's the result. Let me just tell you the results. There are 6 different orbits, and I label them as O minus, O plus, O0, O1, O3, and O6. I'll explain why we have this subscript. And the important thing is that two of these orbits are open. They are 20-dimensional. That's the dimension of the space of three forms. And then there's a 19-dimensional, that's a hypersurface. That's the you can say this is the generic degeneration of the positive three forms. And there are some lower dimensional, more degenerate three forms. And these are their normal forms. And in fact, this open orbit O minus is related to complex geometry, and this was utilized by Hitchen and most recently Donaldson Lyman in their study of, I guess, Calabi-Yau threefolds with boundary. So this normal form is simply just a real part of a complex volume form. So this is basically the orbit we are most related to our case. And there's another open orbit, O plus, it's related to what's called paracomplex geometry. So those are the kind of geometry where you have some operation, you have some like endomorphism of a tangent bundle, which is square to +1 instead of -1. And this is like so it's like the kind of geometry over a different kind of number. It's called paracomplex numbers. And then there's this degenerate orbits, and it's unclear at least what kind of geometry structure you can see in these cases. And now let me explain why these orbits are labeled like this. So instead, actually, we can introduce a few equivariant homogeneous polynomials on the space of three forms. There are four of them. The degree is just 1, 2, 3, 4. And so this input of these polynomials are just some three form, where you can also just think you choose the basis. It's just the coefficient of this basis of the three form. This degree 1 polynomial is just the identity. So the output is again a three form, and this is the definition. The input is phi, the output is phi itself. And there's a quadratic polynomial, degree 2, and its output is in this endomorphism of the vector space tensor with the top form, sixth form. And how is this K defined? Is that if you insert a vector little v from this vector space capital V to the output, it's defined to be the negative of interior product with phi wedged with phi. Just recall that phi is a three form, so this interior product will give you a two form. After wedging with phi, you get a five form. And this phi form can be canonically identified with something as V tensor with the sixth form. So the output here is like in the capital V tensor with sixth form. And this one is linear in the little v, so the K phi itself lives in the space endomorphism of V tensor with sixth form. And this is obviously quadratic in phi. And we can, by using K, we can introduce this cubic polynomial f, whose value is a three form tensor with a six form by this formula. And finally, we can introduce this this degree 4 polynomial, whose value is in the top form tensor square. That's again a line, and it's defined by minus phi wedged with f of phi. F phi is like a 3-form tensor with a 6-form. So we can introduce these equivariant homogeneous polynomials. And all these orbits can be easily characterized by using these polynomials. So these two open orbits are simply the places where Q is negative and Q is positive. And just recall that Q takes value in this space, which is a tensor square of a real line bundle or real line. So it does make sense to say anything here is positive or negative. If something here can be written as a square of something which is non-zero, then we say it's positive. If the negative of that thing is positive, we say that's negative. Okay, so it makes it makes sense to say Q is negative or Q is positive. And actually these two open orbits are the two open orbits we have in the list. So all the degenerate 3 forms in the sense is given by this hypersurface Q is 0. And then if we look at F is this locus of F is 0, then we are just it's the union of the 3 lower. This is like so O0 is like the open part of the hypersurface, and this is given this is like the stratification of all these this like the degenerate orbits. They're given by the zeros of F and K and so on. And these are the subscripts 0, 1, 3, 6 are given by the kernel dimension of the kernel of these 3 forms. It's like you can ask, okay, if there's some vector, if you take the interior product with the phi is 0, then that's called the kernel of the 3 form, which are all the vectors whose interior product with phi is 0. And the dimension of this kernel can only be of dimension 0, 1, 3, and 6. And in fact, you can just use these dimensions to classify all these degenerate 3 forms. So that's why they are labeled like this. Anyway, so these are just some very classical linear algebra, and Hitchens construction can be summarized as follows. If you notice that this Q of phi is negative, that means we are living in this orbit O minus. Then we can construct a complex structure by rescaling the K of phi. So KFI, recall, is that takes value in the endomorphism tensor with the top form. But by taking a square root of Q, you also get something in the top form, and that part get canceled. You just get something that's an endomorphism from V to V. And there's a miraculous identity that if you compose K with itself, it's always a multiple of identity. Therefore, by rescaling it like this, we know J squared to minus identity. So J is a complex structure on this vector space. But the thing here involved is like taking the square root, which you need to first choose an orientation of this vector space V. And then everything would be canonical. Okay, once you have this complex structure, you can construct the imaginary part. It's just you pull back the real part by the complex structure. It turns out the full real part plus I times the imaginary part will be a non-zero 3 form with respect to this complex structure. So that's a complex volume. So this is how you can construct everything from the real part itself. But this real part is not something arbitrary. It has to be living inside this open orbit O minus. And in this case, actually, you can write down this kf, these polynomials very easily. They are just k is like a multiple of the complex structure. F is like a multiple of the imaginary part, and q is like the fourth power of the phi norm is the minus. So these are the familiar case of where we have complex geometry. But now let's also incorporate the symplectic form. So now let's consider a six-dimensional symplectic space and a primitive three form, and we have the corresponding classification of these orbits. What, as you can see, is that what you expect is that the orbits O minus and O plus, they now split to some more refined orbits, and we have all these normal forms. And because we have this symplectic form, we also have this canonic volume form, which is a sixth form. So in this case, we can think of K, F, and Q are just as endomorphism of V, three form on V, and scalars. It's because all this top form part, they are canonically trivialized. So we are just thinking of them as endomorphism, three forms, or just scalar function. And the orbits concerned with we are carrying is those from the Calabi-Yau geometry. So in that case, it's O minus plus, where we have this signs, right? Signs, and these orbits may degenerate to O0 plus. And this plus means the corresponding metric may be positive definite, or in other case with signature. So anyway, after this preparation of linear algebra, we know the following is equivalent. Is that if phi is a real part of a complex volume form, is equivalent to that phi is a positive primitive three form, and this is equivalent to phi belongs to this orbit for some parameter mu. And this mu basically is just like the norm of phi. And our setup is that on this fixed symplectic manifold, we consider a family of Calabi-Yau structures determined only by the real part, and they are themselves Ricci flat, and we assume that on the open dense subset we have a smooth limit, and this limit is a degenerate three form that belongs to this orbit O0 plus. So that's the generic degeneration, actually, because this is like the hypersurface. O0 is the hypersurface. So you don't degenerate to the lower dimensional orbits. It's like this is like the most non-degenerate kind of degeneration. And what we want this to be, this is a pointwise condition. If it's degenerate to the like 0 or other more degenerate orbits, you can throw that locus to the complement of M circle. So that's okay. So this is like this belonging to this orbit is like a very generic assumption. And our goal is to study the geometry of this triple. It's like M circle, omega, and the phi 0. Now we can forget about the family. We can just study the geometry of this limiting structure. And before continuing, let me give you some examples. A basic example is, this is like a toy case, is that we have this elliptic curve, as C quotient out by a lattice with period tau. And this is like the complex description. So with the same like complex volume form is like dz. But we can identify this with the same real torus R square quotient by Z square, but with a different complex structure J tau. And this J tau is determined by a holomorphic one form dx plus tau times dy instead of dz, which is dx plus I dy. Okay, and there's a standard symplectic choice of symplectic form is dx by dy. So this is like it's like how we pass from the usual algebraic geometric setup to this more differential geometric setup by choosing the gauge. And the first example I want to discuss is that we have just three copies of this elliptic curves with the same period tau. And the product has the product symplectic structure and complex structures. But we should think of each of E tau as the standard real torus with a complex structure determined by tau. And then we can choose this family of holomorphic volume form. This is just the product of this 1, 0 form there. And we normalize this by tau square. Tau is a parameter in the upper half plane. And we can take its real part, and where t is tau is I over t, where t is positive. So you can think of we're just going in the imaginary axis of the upper half plane. And if we take the limit of this family, we get this standard degenerate three form in the orbit O0 plus. And but as expected, this limiting geometry here is flat. So this is like this three form here is a degenerate three form, and all the geometry there are flat. It's like you'll get some flat three-dimensional torus vibration over a three-dimensional base, and there's no singularity. So this is like the one simple example of where we can actually achieve this convergence. But this is not the interesting case because the geometry here is flat. There's a more complicated example where we can build up such a convergence from an elliptic fiber K3 surface and an elliptic curve. And in this case, you can also take the limit of this real part by choosing these the holomorphic volume form carefully, which is like this. You can take the limits of the real part, and this convergence only happens on certain locus of it's away from the singular fibers in this elliptic fibration. And this is like a non-trivial example of such convergence, and the geometry here is not flat. So, but our goal is not to, I guess it's just to say, what can we say if we have such setup? And so assume this convergence, we need to introduce some integrability conditions for three forms. There are a bunch of natural choices, like you can say the three form is closed. I'll just call it integrable, means it's closed. We can say consider what's called the K integrable, means this K phi as endomorphism of the tangent bundle. Its eigenhuge tensor is 0. And we can talk about F integrable, where it's the F of a phi, which is another 3 form, is closed. Or we can consider a Q integrable, which says the Q of phi, which is a scalar function, is closed, which means it's a constant. So these are some very natural integrability conditions you can impose on 3 forms. And the main theorem is that if it is both integrable and F integrable, it implies all other kinds of integrability conditions. And so we introduce this definition as on a symplectic 6 manifold, a primitive 3 form is called F harmonic if it is both integrable and F integrable. Because this 2 conditions is somewhat like this 3 form being a harmonic form. It's just there's no hot star. Instead, we work with F of phi instead of the hot star of phi. And these are the right integrability conditions, because if it comes from the Calabi-Yau structure, if this 3 form comes from the actual Calabi-Yau structure, then being F harmonic is equivalent to being Ricci flat. Therefore, under our assumption, if we assume we have this kind of convergence, which is, let's say, C1 or smooth, and we assume this family comes from Ricci flat Calabi-Yau structures, then the natural integrability condition to put on phi 0 is just being F harmonic, because it's just some first order equation satisfied by this 3 form, and they pass to the limit because this convergence is assumed to be smooth. So the F harmonicity of phi t implies the F harmonicity of phi 0. So what we are going to do now is to study the geometry of this triple M circle omega phi 0, where phi 0 belongs to this orbit O0 plus pointwise, and it is also F harmonic. And I will call this kind of geometry nilpotent Jordan Calabi-Yau geometry. And it's called nilpotent Jordan is because the K, this complex, something like complex structure, now they square to 0, but they are not diagonalizable. They're Jordan blocks. Okay, so that's just my definition of the nilpotent Jordan Calabi-Yau geometry. And the theorem is that this K, which is the endomorphism of a tangent bundle, which you can construct from this 3 form by this is like K is like the equivariant homogeneous degree 2 polynomial I mentioned. It's an endomorphism of tangent bundle satisfying its kernel. It has a 3-dimensional kernel, and its kernel is same as its image, so K squared to 0. But its kernel is only 3-dimensional, so it's not diagonalizable. And in fact, this kernel is a Lagrangian subbundle of tangent bundle. And moreover, the eigenhedge tensor of K vanishes. That's from this, because this phi is also K integrable. And from this condition, you can derive that this Lagrangian subbundle you have is actually a foliation. So this is a involutive distribution. So you can have all these lives, which are Lagrangian, immersed Lagrangian submanifolds. So the conclusion is that Lagrangian, at least foliations with singularities, arises naturally from our version of degeneration of Calabi-Yau, just from the degeneration of this real 3 form. And these singularities, you can think of them as just the place where the convergence fail.
Sorry, just to be sure, is it a Lagrangian foliation of like the tangent space of M rather than M itself? Is that correct?
So you have this Lagrangian subbundle of the tangent bundle, and it's involutive, which means on each point on the manifold, there's a maximal integrable manifold, whose tangent bundle is given by this bundle. this
Yeah,
Lagrangian
okay.
bundle. So
So
there's
from that you get a Lagrangian fibration of the M circle.
it's not necessarily a fibration. It's this leaves. You can think of, you may have a like real two-dimensional torus, but this Lagrangians are just some one-dimensional line, but these lines may be dense in the torus. So these are only foliations, they are not fibrations. If you have fibrations, all these fibers are compact or at least not dense in the whole space. But these foliations, they may be more irregular in the sense that you have a three-dimensional object that's immersed into this six-dimensional manifold. But if you take the closure in the six-dimensional space, it may get the whole thing. So this leaves may be dense. That's
Great.
the difference from foliation and the fibration.
Yeah, thanks.
Otherwise, it's just like foliated by these three-dimensional Lagrangian submanifolds. But these submanifolds, they are only immersed. They may be dense.
I was also going to ask if you have any understanding of what F harmonic means in terms of, well, you had some physics motivation that you were considering at the start. If there's any,
This is actually a natural condition. I'm not sure if it's so in the type 2a equation, the type 2a equation, one of the equations is exactly d of this f phi. So one of the equations phi is closed, that's d phi is 0. The other equation is d of f phi is given by this Poincare dual of this Lagrangian brane. That's the equation. So this dfi equals Lagrangian, the Poincare dual is more or less like a delta function supported on this Lagrangian brane. And so that's somehow very similar to our situation where we want this to be 0 instead of a delta function. So in that case, it's just 0 almost everywhere except for this Lagrangian.
do the other
Right.
functions Q and K also show up in the equations of motion of type 2a?
They can be they are hidden. So this K is basically a multiple of the complex structure. And the Q is like it's just like the norm of phi.
I see.
To the power 4. So these are you can hide them in complex structure or others or just metric. So
But the F is explicit, you say?
yeah, but their expression is explicit.
But you also mentioned it's equivalent to Ricci flat, which itself is a
If it's compact, and then it's equivalent to Ricci flat. Yeah.
Can I ask one more quick question?
Yes.
So if your family phi t on M already admits a Lagrangian fibration, then when you pass to the limit, is the limiting object the same as this foliation that you get, or can it be different?
I don't know, because I think even you fix at least locally, I believe, if you this Lagrangian fibration, they can be deformed. So what I'm trying to convince is that what we can produce here is actually some canonical Lagrangian foliation from this convergence. It's not from the it's not something you have to to search for. It's like
so
it's
if it was a
automatically
theorem, it would have been like any Lagrangian fibration you pick, it should converge to that Dylan. Because before taking the limit, your fibration is not kind of preferred. But after the limit, Teng is producing a preferred one.
Right.
Yeah, I guess I'm just wondering exactly from this point, then if you go backwards, what do you get? If you get, does it recovers? Can you recover something close to the limit?
What I can say is
all
that
of them?
in this example, you do get what you expect. It's really the hyperkähler
Right.
rotation of this elliptic vibration
Right.
with some extra. Yeah. But in general, I don't know the answer.
Thanks.
Okay, so this is where you get the Lagrangian foliation, and you also get all this package in the almost everything from the SYZ package. Like you have actually a induced Riemannian metric on this lifts, and there's a pair of affine structure on the lifts. And one is given by the Bose connection, and the other is determined by this K. And there's a natural Hessian metric. This induced Riemannian metric actually is a Hessian metric with respect to this pair of affine structures, and actually their volume form is parallel. So it solves the Riemann-Roch equation on the fibers with constant right-hand side. But this is not what we have in the SYZ, because on the SYZ, we want something on the base. But you can show that this metric actually has non-negative Ricci curvature. So if leaves are all compact, they must be flat. So, but you do, so that's to say, if you have actually you know the foliation is a fibration, then naturally you get this semi-flat metric. And also, if we know this foliation is a fibration, actually we can produce a canonical isomorphism of a tangent on the base to the space of, this is isomorphism of a tangent space at X to the base to the space of harmonic one forms on the fibers over this point. So Lx is Lagrangian torus fiber over X. And this isomorphism allows us to define an L2 metric on the base. And by using real periods of the torus, and we can define an affine structure on the base, such that this L2 metric is a Hessian metric with respect to this affine structure. And this is basically repeating what Hitchen did in his study of a moduli space of special Lagrangian manifolds. And but the local potential of the Hessian metric solves this Riemann-Roch equation on the base if all the fibers of this Lagrangian vibration, they have the same volume. So those are, let me be very quick because I'm over time already. So I'm just saying that if we consider this setup of degeneration of Calabi-Yau structures, if we have the right, we assume we have this kind of convergence, then from this convergence we can naturally produce almost all the geometry expected in the SYZ conjecture, except for the special Lagrangian condition. And then there's still some open questions there. How do we know if such a limit exists? We only have some examples at this moment. And when do we know this is a fibration instead of a foliation? And how do we distinguish there's different kinds of singularities and so on? But the point of my presentation, I guess, is to say, okay, in this setup of degeneration of Calabi-Yau structures as degeneration of three forms, the SYZ conjecture, the SYZ geometry seems very natural and canonical. So we don't have to search for like Lagrangian foliations or Lagrangian vibration. And that's the end of my talk. Thank you.
Thank you.
Yeah, thank you. Do we have any questions?
Yeah, can you say something more about the special Lagrangian condition? I mean, does it have any interplay with this limiting object that you get, this limiting Lagrangian foliation?
So there's some technical difficulties because if we have this convergence, the limit is a degenerate three form, which doesn't give us a calibration. So if you restrict this three form to the Lagrangian subbundle produced by itself, it's actually 0. But it doesn't have like imaginary part, which is a volume form of this. So it's hard to talk about special Lagrangian if just look at this triple. Because actually, I guess I'm sorry. I want to say is that special Lagrangian condition at this moment is not well defined if we only have this data. So we have to go back to this family of Calabi-Yau, genuine Calabi-Yau structures to talk about special Lagrangian condition.
What happens? I guess maybe I'm asking what happens to the phi naught, so the phi t hat in the limit.
Well, the phi t limit hats usually they blow up. It's like so if we have this kind of convergence, actually f of phi t also converge to f of phi. But f of phi t is just phi t hat times phi norm square. But phi norm square in this case is convergent to 0. So basically this is saying phi t hat behaves like some very degenerate three form, which is like the volume form of three-dimensional space divided by something going to 0.
I see. Thank you.
Yeah.
Are there any other questions? I have a question. Probably the answer is similar to the special Lagrangian case, but do you think there would be a similar way to, rather than finding a Lagrangian foliation or fibration, say to find holomorphic fibration like K3 Lefschetz fibration in the Calabi-Yau threefold case from the limiting data?
I don't know. I'm sorry. I don't know.
Also,
sorry, maybe I can ask a related question. Is it possible that an interpretation similar to the one you have for Lagrangians, already expressed in terms of these polynomial invariants, would then correspond to the kind of holomorphic fibration structures that someone was talking about? Because you focused on one of these invariants, and that gave you the degenerations corresponding to Lagrangian foliations and hopefully fibrations.
Mm-hmm.
And you have a classification. So
you mean other invariants?
Yeah, whether it's K or F or I mean, you used one particular
right.
Such.
It's because the other polynomials actually they contain less information. It's like so if for most of the cases for all the other degenerate orbits, f is 0. So it's only the orbit we are talking about, f is not 0. But in this case, f is just like f of phi is just like the volume form of this Lagrangian foliation. So you can still see the Lagrangian foliation from f, just it contains less information. You don't see this matrix and the other objects.
Oh, you don't see metrics at all.
Yeah, you only see the Lagrangian subspace. You don't see the induced metric.
Oh,
So strictly speaking, like K contains more information than F.
Mhm.
And Q is just some scalar function, so we
So the
cannot
answer is
detect
essentially the
anything.
same answer to Dylan's question.
Yeah,
I asked because I mean I was hoping there would be a G2 version, but this is like the same difficulty, I guess. Do you hope that would be a case that you can get some vibration for G2?
I think maybe co-associative vibration
But
is what you
co-associative is
expect.
more like say it's a bit more like special Lagrangian than Lagrangian, something weaker than maybe co-associative without co, but not associative.
Well,
Yeah, I don't know, but what I know is that there's also a classification of 3 forms in 7 dimensions in all these orbits and all. And so yeah, so you can just play with it.
Yeah.
but there are some cases. So in the co-associative case, there seems to be, the reason I asked about the degenerations, like looking at the vibration under the degeneration, is in some cases in the limit, you get something which is sort of just limits to like a flat vibration on C3, sort of a classic kind of Lefschetz type vibration. But in other cases, it seems that the limiting geometry is a little bit more complex. And that seems to correspond to when you, on the G2 manifold, you don't really get a vibration. You really get something which is kind of more like what you described, where you just have to remove some locus and then you get these co-associatives, but they might intersect, like in 2-dimensional intersections and so forth. So I don't know, maybe there's maybe something similar is going on in those cases.
Yeah, it's possible, but I haven't explored anything in G2.
Yeah. So back to the Calabi-Yau threefold case, and I may have missed this. My audio went out for a while, in particular during most of the question time. But have you looked at what happens under the mirror symmetry proposal in terms of mirror duality relating your degenerations and possibly the foliation and vibration structure?
No, I haven't thought about that. It's I guess it's too complicated for me at this, I would say.
Okay. Yeah. I mean, in the case where instead of it being these kind of degenerations, where it's complex structure degenerations in an algebrogeometric setting, and instead of Lagrangian foliations or vibrations, it's holomorphic vibrations. This fits into this framework I have for mirror symmetry with Harder and Thompson. And it would be very interesting to see, in terms of Salman's question, whether from this approach to degenerations you're taking, the holomorphic vibrations would show up naturally, or the degenerations in the sense of complex algebraic geometry would show up naturally.
So I guess this kind of degeneration I'm talking about is more like what the picture you have for like geometric quantization. It's like if you think of this complex structure as a complex like quantization, this is like this complex polarization. You have these holomorphic directions and anti-holomorphic directions. Both of them are just like Lagrangian subspace for the complexified tangent space. And these two, when this direct to like Lagrangian foliations, or they collapse to a real one, that's basically going from this orbit O minus to O zero. And this orbit O plus is actually a pair of transversal real Lagrangian foliations. And they can also collapse to a single real one. So this is O zero is like the common boundary of O minus and O plus. Yeah, so but
well, you did a nice job of motivating with the triple product of elliptic curves. And I'm wondering, have you pushed this through to orbifold Calabi-Yaus, where you get closer to sort of honest Calabi-Yau threefold geometry by quotienting and resolving?
Yeah, I think that's possible, but I didn't do anything.
No, it's exciting. It's an exciting approach.
Yeah, I'm spend more time, I guess, thinking about how to incorporate the special Lagrangian condition
Right.
at this moment.
Yeah. You got John Lofton there, right?
Yeah. John Lofton is my colleague.
Yeah, absolutely. You know, John and I were in grad school together, so no, he's a great resource for anything like that.
Yeah.
Good. Well, thanks so much.
Okay,
Thank you.
do we have any other questions? If not, let's thank one more time.
All right. Thank you.
Thank you for a great talk.